Okay, good morning everyone. My name is Mathias Bonduel and I will give the next presentation. It's titled Including Widespread Geometry Formats in Semantic Graphs Using RDF Literals. And it's building on the work of Anna. Anna Wagner presented the presentation before me. And we collaborated to extend the work that she did in her presentation. So an outline of the presentation. First we'll give an introduction of geometry and linked data. So building on the work of Anna Wagner. Next we'll talk a little bit about the technical details about RDF literals. Third part will be about the practical requirements for geometry, and we will see if it's possible to solve them using technologies such as linked data for this. In the fourth part we present a data modeling approach and the ontology named FOG, which extends the OMG ontology of Anna Wagner. And in the fifth part, there's a sample data set and demo application to be discussed, followed by a conclusion. So as Anna already discussed, we can have, for example, objects. This can be a building object, a building element, a building space, whatever. And it can be connected to geometry descriptions. The geometry description can be RDF based, so actually a graph describing how the geometry looks like, what the geometry is, or it can be, let's say, a snippet, so an embedded geometry file, or it can be a reference to a file external to the graph. For the two lower methods, we can use RDF literals, or at least that's the assumption. And this will be discussed in this paper and presentation. What OMG discusses and provides is a uniform and flexible linking method using two properties. So a property between two nodes. OMG has complex geometry description and a data type property to connect an object and a literal. So the technical parts. What are RDF literals and how are they defined in the W3C standards? They typically exist, they consist of three parts. So the first thing is the literal value, and this is the actual content of the literal. This can be a string, this can be a boolean, a double, etc. The only rule is that everything that's inside the value has to be Unicode characters. So if you have binary data, you have to encode it. The second part is the data type. And data type explains what kind of data is to be expected. Is it a string, is it a boolean, and so on. And finally, there's the data type property, which connects a node to a value, a literal. And this gives more information about the type of relation between both things. Okay, what are actually the practical requirements for geometry? So that we can check if the literals approach with RDF literals are valid for our cases. The first one is to allow every type of existing geometry schema. This might seem like, let's say, a high goal, but it's necessary because we have so many different geometry schemas. A lot of people are using different formats for good reasons often. For example, if you want to visualize geometry on the web, in a web viewer, you need certain formats, while if you were doing parametric geometries, you need other formats, for example. We want to be able to mention which geometry schema is used from the graph, so that if you have an application that it can call for the right information that's supported by the application, so that the data transfer is limited to the things that the application can use. We also want to relate with geometry schemas that are closely related, such as, for example, a certain schema can have multiple versions. Some of them might be quite different from previous versions, but we want to be able to group them. Because, for example, some application supports all kinds of DVG versions. Let's say the newest AutoCAD version supports all DVG versions, while older AutoCAD versions only support the, let's say the older DVG versions. Some geometry schemas also have associated files. Good examples are material files and textures, and we need to be able to say that a certain geometry description goes with a certain texture. So these files, these descriptions have to be grouped. And finally, as already discussed by Anna and also during the question, we need to be able to add metadata for individual geometry descriptions. This can be, for example, the geolocation. This can be the up axis. So in some CAD software, the user is free to choose the up axis during transformation and so on. And this can be really a nightmare if you want to combine a lot of different geometry from different stakeholders. This brings us to what we propose as a data modeling structure and the supporting ontology to do this. If you look at RDF literals, we have the three parts: the data type, the data type property, and the literal. So as discussed earlier, the literal has to be Unicode. So this would say this limits us to not use binary data, but of course you can always encode binary data to store it into literals. The thing that we propose is that we can use the data type here to express which kind of method is used to store the geometry in the graph. So for example, in the first case, if we embed geometry, so as snippets into the literals, we copy the entire content of a geometry file that would exist normally in your computer, and we place it into the literal. So we use the data type string if there's no encoding. For example, in OBJ, it's a text format. We don't need any encoding. But for example, if you would use DVG binary format, we need some kind of encoding. And in this case, we can then use the data type to express which kind of encoding is used. Is it base 64? Is it hexadecimal? Or is it some other encoding? And then the other method, if we reference external files, we can use the data type XSD and URI to reference to local files or to files online. This leaves us also the data type property, and the data type property can be used to define the geometry schema that's used. And also, more importantly, we can be very specific about it, which version of the geometry schema is used by having very specific data type properties. If we want to group associated files, associated RDF literals, we need to have OMG level 2 or 3. So at least one intermediate node in between is necessary to be able to say that a certain material file has to be treated together with the certain, let's say, central OBJ geometry file. That these two belong together and that the material file doesn't belong together with the other OBJ file. Having OMG level 2 or 3 also allows us to add metadata, for example, to add information about which up axis is used. This was all about the, let's say, the data structure and our proposal to use certain parts of RDF literals. But we also need to define the data type properties inside a data structure, an ontology. And we define this as an extension of OMG, and we call this the File Ontology for geometry formats. Here is some extra information, such as the namespace, and of course, according to best practices in semantic web environments, we also we offer a persistent URI as a namespace for the definitions that are defined in this ontology, and this redirects to the raw ontology for machines and to the HTML documentation for humans to understand the data structure. This ontology is also a community effort because we cannot, let's say, have every existing geometry schema already in there from the start. There are so many different geometry schemas that exist. So as a community effort, we would encourage everyone who wants to use this kind of ontologies to engage in it and to mention if you miss certain geometry formats or versions of geometry formats you want to use. It's easy to add them to the schema. The schema itself has to be understood as a taxonomy form, and it extends the two properties from OMG. So OMG has simple geometry description to connect to RDF literals containing an embedded geometry or geometry that's referenced inside the literal. or OMG has complex geometry description for geometry descriptions that are RDF based. Then the next level, we define a sub property, which is schema specific. For example, fog as GLTF. And then we go to the version specific property, GLTF version 1.1 or 1.0 more specifically. And in some cases, we even have a fourth layer, which is defining a file extension, because certain schemas have multiple files. For example, in this case, GLTF can have the GLTF JSON, but also can have textures and shaders and so on. Okay, let's look at some sample data. Also, a good practice when you publish data structures is that you at least give some sample data. In linked data terminology, this is called A-box, compared to T-box for the terminology, which was discussed earlier in this presentation. We define, let's say, a sample graph which defines and explains how to use these kind of structures. We also use Sparkle Visualizer as a tool to express how these data structures can be used with using the same sample data sets combined with example queries to query data, to create new data triples and so on. I think this will be very difficult to read and to view, but this is an overview of the sample data sets. It contains 2 columns consisting of 3 parts, base, shaft, and capital. And we use different kind of geometry formats and so on. So in this visualization, we kept everything, all the literals are dummy data here, but we of course also have the data set with the full literals online to be used as testing. Then we also made a web application to demonstrate how this can be used. The web application works as follows. It has a request handler which sends a Sparkle query. Sparkle is the query language for linked data. Sends a Sparkle query to the RDF triple store, so a database for linked data, which contains the schema, so the File Ontology, and the A-box, so the actual triples with content. It will respond with a JSON response and send this to the request handler, which will trigger the right decoder based on the data types that are returned for each literal. And in the next phase, the data type properties will trigger the right geometry loader to either visualize the geometry, and in our case we use 3JS to do our web visualization, and for other geometry files to be able to download them to a file to your computer. This is a screenshot of the application. So we are able to visualize in 3JS. We had loaders for OBJ, POI, GLTF, POI binary, GLTF binary, and Collada. We're not able, for example, to load step geometry because there's no such loader in 3JS. And the same for E57, which is a point cloud format. So this is also one of the use cases that is more interesting for me. I work on heritage buildings, and in my case, I have point clouds, and I have simple geometry descriptions. I have very complex geometry descriptions for different cases, for different reasons. I need to be able to say that certain geometry is derived from point clouds in a certain way. And in this case, I can use OMG for this. This brings us to the conclusion. So RDF literals can be used to embed geometry files and to reference to external files. So everything that's already in the standards can be used for this. And I can use this for any geometry schema that already exists. It can be 2D geometry, it can be 3D, it can be text or binary, it can be open or closed, doesn't matter actually. As long as you have the application to handle your geometry, you're fine. But this has the, let's say, important consequence that you can use any existing geometry schema that exists, and also, as a consequence, use the applications that can work with these kind of geometry schemas. We don't have to reinvent new geometry schemas to be able to do our work. We also propose a uniform and flexible data structure, extending OMG, of course, with modeling patterns, and of course, the taxonomy to be very specific about which geometry schema you use. And we provided sample data sets and demo application, which is online. In our future work, we would like to add terminology for defining metadata. This can be up axis, scale transformations, georeferencing, file size, and so on. So we're currently working on this. There might be also, in the case when you embed geometry files inside literals, there might be a case that the literal size can have an impact on the performance, but this really depends on the kind of database you use, how the database is implemented. But at this point, we don't foresee big issues, so we did some preliminary tests, and the way databases handle this is pretty optimized. So this is not really an issue, probably. We also would like to have support for spatial querying inside graphs. This already exists for 2 extensions named GeoSparkle for 2D well-known text and GML geometry descriptions, and BIMSparkle for 3D well-known text. But we would like to extend this to other geometry descriptions. And finally, we would, of course, have to, if you define ontologies and so on, data structures, you would like to have people to reuse them. That's why we also document them, try to document them very well. And it would be interesting to see them reused in applications focusing on linked database, BIM, for example. We have, for example, IFC to link building data converter, which can convert IFC to RDF graphs according to the link building data ontologies, such as BOT. And it would be very useful if it would also include geometry, of course, which is not included at this point. So this was the presentation. Thank you for listening, and if there are any questions, I would be happy to answer them.